turn it on and off. Привет. Okay? Okay, thank you very much for coming. Let's begin our workshop. So, just for our invited speaker, I should explain this is actually already fourth workshop in a series roughly called Constructive Knowledge. And Constructive Knowledge is a project with several people, with little funding. And just one semester we are making this workshop. Different people actually were doing not exactly the same thing. The general idea is somehow to make explicit. Official title is epistemological and logical aspects of constructive knowledge. So constructive knowledge, I'm thinking something first related to knowledge representation as in computer science, and some, say, logical background and epistemological underpinning. Constructive meaning both in more technical sense, what many people here are doing kind of constructive logic. Me personally was working with homotopy type theory, there's univalent foundation from that side. But also I think constructive just as a way really making explicit in the form of some procedure what we need really in computer science for, say, many things that we talk in philosophy, say, less formally, and we want it to construct it, make it work somehow, right? Not only traditionally on the paper when many things kind of going without saying, but more explicitly. Okay, so today that's rather general idea of the project. I will not elaborate much, it's I think less important. So I'll try to talk today about justification in knowledge representation. Meaning knowledge representation both in technical sense of computer science and say more generally as a general epistemological problem. And actually I'm trying to put these things together a little bit. So I a little bit looked into knowledge representation literature, even I'm not an expert. Sergei Kovalёv is much better expert in that field than myself. But I just trying to put ends between, say, philosophy and discussions which are going on and some philosophical logic and, say, computer science. That's the general idea. So I'll talk first about some, I say, generalities, that will be rather limited, but anyway, about justification. Then I'll talk about, actually that's early paper by McCarthy and Hayes of 1969. One, I think, of first paper, maybe the first paper, if I'm not mistaken, philosophy of artificial intelligence. So, and I think they really brought a lot of philosophical foundation, even if they didn't want to, right? But they did, as a matter of fact, and explain why. And then I will talk also briefly, and I hope it will maybe connect to Tudor's talk, about two alternative semantic logical inference, meaning, say, standard denotational model theoretic, Tarski style semantic, and what is relatively recently called proof theoretic semantics. And I'll try to show that that's really difference which underlies a lot of developments in knowledge representation, at least on kind of ideological level. And that's very briefly. I think I will not really have time to introduce in full univalent foundation, but I try to give some hints how it can be used as a model for knowledge representation. And by the way, it otherwise looks as kind of update, because these people, they actually looked into foundation of mathematics of their time, and so it's kind of natural to look at something new in foundation mathematics in our time to make a progress. So generalities about knowledge, I will use a very standard definition of knowledge without going to discussion. only maybe some little comments, as justified true belief. That definition actually it's limited in the sense that only applies to propositional knowledge, because we talk about truth, right? Truth of propositions. And actually in that context is particularly becomes important different sort of knowledge, which is called knowing how, knowledge how, procedural knowledge, so knowledge of particular rules. And I'll come maybe at the end, because I think that Univalent Foundation gives a particularly good model how to relate these two kinds of knowledge and put them into a whole, if you like. Right, but so far I'm concerned just with propositional knowledge, with true belief. And very general remarks that truth is objective notion, as you know, this older generation of philosophy used to say in this country particularly, in the sense that it does not depend on anyone's epistemic attitude or anything else. It's kind of truth of the matter, as we say, right? Belief, on the contrary, is subjective in the sense that, no, at least some prima facie is simply refers to particular epistemic agent, individual. Normally we think of human individual and his or her brain state or whatever, however you describe epistemic belief, but something really refers to individual. In computer science context, we would say individual user, right? And justification, which in that talk I will not really distinguish from proof. It's something that relates to things, intermediates between them in a sense, an interesting way, because in one sense it also objective, so it's a subject of some validation procedure, right? We may say that's really valid justification, this is not valid, there's nothing subjective, but at the same time it's supposed to somehow persuade to generate belief, all right? So it has both these features. And now, Sergei left, unfortunately. As I say, I don't have expert knowledge of this modern knowledge representation technology, but still is my impression, and I will be happy if some of you correct me, is that it's a problem about justification in existing system, in the simple sense that such system simply don't provide users, individual users, with anything like explicit evidences in support of those truths or knowledge that such systems are supposed to convey to users, right? So what I read in computer science literature, knowledge is understood basically as kind of sophisticated structure. So there are raw data which actually alone are kind of truth bearers in that context, right? They are supposed to be recorded from, I don't know, telescope or street camera or whatever. So they are really truth bearers. And anything else that is called information, knowledge in that context is just this kind of way of structuring them, making them kind of user-friendly, doing something with them, which is supposed to preserve truth, in a sense, right? But justification is not simply about truth preserving. It's, of course, necessary, but not sufficient for qualifying as justification, because justification needs somehow also work, as I explained, as generating beliefs, right? So it's not just in some, I would say, absolute sense it should preserve truth, but it should convince the user to generate the knowledge. And that is a task which I think it's not simply addressed in most of the system. And why I think it's particularly bad, first it kind of engenders public character of scientific knowledge and increases the role of epistemic authority. So a user of such a system, basically first he or she realizes he should believe those people who prepared the data, right? Then he or she should believe that those data are really preserved, they are not corrupted somehow, right? And second thing, you should believe all these computer engineers who somehow designed these systems which are supposed to convey truth from the data to him or her, right, to her interface. So it's all absolutely opaque, right? And such a user has only choice to believe all these people that they are doing everything right without having any means like access to this. Usually user doesn't have access to raw data, no anything, right? There is nothing, as far as I know, specifically designed that would allow individual users, say, check what, say, the system says you some proposition P, but I want to prove, I want to check, right, somehow. And I think that's really, no, of course it should be kind of technical challenge, but I also think that just such system, somehow this architecture, and that I'll try to show, of such system simply doesn't have place for such sort of technologies. And after all, it makes knowledge less reliable, I think, because this public, checking, cross-checking is something that make knowledge actually reliable. And then, of course, there are all these talks that we cannot believe what we read in our screens and so forth. So I think it's in this general epistemological term really a problem, right? No, and what I say, I imagine it's a system which would provide individual users with evidences justifying propositions, and that may include, I just kind of fantasize, kind of certified access to raw data. So I want really to go back to data and some guarantees that they are well preserved. No, I had other ideas, say, in simple education and science education, elementary, right? In my time, we made a lot of experiments in school, you know, so we could see how this stuff with electricity, with mechanics. And I have impression that today it's more and more replaced by kind of computer simulations, right? And again, I think that's bad, not in the sense that screen is somehow, worse device than, material objects, but for more serious reason, because a child or a person simply does not have, all children know, even my little kids already know that you can see all stuff on computer, right, all fantasies, and so there is no really difference between fantasy and reality. And I think that's important. I like fantasies, but I think that difference is very fundamental. Still, we cannot just get rid of it. It would be absurd. Right. And, of course, it's a very, very, very broad problem, but I think a part of the problem which somehow I may be better in place to speak about, because it really depends kind of philosophy, right? Kind of philosophy of behind designing of these systems, and so that's why I think that this kind of philosophical discussion may probably give a good idea how to change the technologies and give some new interesting direction. And then actually I'm not going to invent something really new, because actually we are talking here about two different conceptions of logic. One more or less mainstream, and I explain what it is. And the other, it's roughly maybe described as constructive, intuitionistic, going back to many people, to Gensen, to Brouwer in a certain sense. And actually, I'm not trying to do here the full history. I'll refer to works by Doug Private. Then if someone interested in history, there are good historical papers who try to construct it as a longer tradition. But I think that alternative approach So the claim is that in the current design of artificial intelligence and knowledge representation, that mainstream conception had been used, even maybe without full analysis of its implication, and so kind of suggestion used this other one. And moreover, there is an additional reason for that, because as I'll show, it's kind of more computer friendly. There are features of this constructive understanding of logic which make it more directly and more easily implementable in computer. So there are even more reasons to use it. So that paper that I already mentioned, it's called Philosophical Foundation. No, the name of the paper, I didn't put it here. It's called Some Philosophical Problems from the Standpoint of Artificial Intelligence. That's that way. And so here is the quote. The right way to think about the general problems of metaphysics and epistemology is not to attempt to clear one's own mind of all knowledge and start with cogito ergo sum. Instead, we propose to use all of our knowledge to construct a computer program that knows. That's rather interesting. So at the very beginning here, the authors, McCarthy and Hayes, they do have this epistemic concern, even if it's a little bit strange in my view. So they're really serious about, they're thinking not about human knowledge, but somehow even they're talking about very simple things. There is nothing very much advanced here, really. But they still imagine that program knows something, right? But I think their idea, they don't make it very much explicit, is somehow that if we construct knowledge and we may attribute it to a program, that somehow give us better model of what is human now. Maybe that's their thinking. But anyway, right. And then that is continuing the quote. This point of view corresponds to the presently dominant attitude towards the foundations of mathematics. We study the structure of mathematical system from the outside, as it were, using whatever mathematical tools seem useful instead of assuming as little as possible, instead of this Cartesian paradigm. So they say explicitly they want to do something similar to what is going on in foundations of mathematics. Now, but actually, I'm not really sure they really do. I think there is a lot of confusion around it. And I explain. So after all, say we want computer program that decides what to do by inferring in a formal language, and by formal language, then later make explicit just first order logic. In a formal language, that a certain strategy will achieve its assigned goal. A method is given of constructing a sentence of first order logic, which will be true in all models of certain actions, if and only if a certain strategy will achieve a certain goal. And right, then they continue, they say, since the program makes this proof, it executes the task. And no, my comment is that that's actually very, very bizarre if you think about this. Because what is a proof that certain strategy achieved a goal? No, I would say easy and probably best proof is just achieve this goal, right? If you achieve this goal, you proved that you achieved it. But apparently they have something different in mind. So they want to supply this program with this first order description, whatever, right? And some deductive system which, in a sense, without executing the task, right, it somehow proves that it's executable. You see? And I'm not sure, I think from computational viewpoint should be very, very hard and somehow uneconomical. Maybe that's what they mean, that that program does not simply do what it should do, but also somehow knows what it is doing. What they probably may mean this here, right? And also it's interesting, what they call meta-mathematics. I think there is kind of confusion. Because here apparently they, as a meta-theory, they mean this first-order theory, right? Which is about what is computable, what is not computable, so forth. Which they want to implement somehow inside. But of course in foundation mathematics it's actually different. It's first-order logic is supposed, even maybe not quite justifiably, but it's supposed to be language of mathematics, right? And meta-mathematics is supposed to be just usual mathematics. That's very, very tricky because in the beginning of the project, when Hilbert and Bernays invented the term meta-mathematics, what they wanted some minimal, finitary, ideally, piece of mathematics, which would be sufficient to prove about first-order formulas that certain things are provable, not provable, certain theories are consistent, certain others are not. Right? No, then we know there were, say, accurately problems with Hilbert problem about Gödel, etc. What really happened that people, of course, they continued this, and as do they today, this meta-mathematics, but they didn't have this restriction. It is no longer supposed to be minimal, all right? No, something like continuum hypothesis, this forcing proof, right? There is no restriction. Forcing is just a piece of usual mathematics. What is not, what is specific about this proof? It's this kind of object, and object is Zermelo-Fraenkel set theory, right? So here, object theory is a first-order logic, right? And meta theory is just whatever you use. And here, if I understand them correctly, they use first-order logic as kind of meta theory, and that's different. That's not. No, anyway. No, anyway, what actually it's interesting in their paper because to apply this first-order language to something like computing, they need kind of intermediate language, right, of operations, and that intermediate language looks much more like functional language, right? It's about application. They are not using like lambda calculus, they are just kind of finitary automata, but which is basically simplified version of the same, so it's all about application. But on the top of that, they put first-order language for proving that certain, say, strategies exist or don't exist. So they are not trying to make logic into this, computational level. It's supposed to be kind of above. And that's, I think, under that conception, we really, what I began, that problem of justification simply, evaporates. And the reason for that, at least philosophical reason, if you look what logical concept, actually, this McCarthy refers explicitly to Tarski's logical constant correlation when he speaks about truth in all models, right? So according to Tarski, we have this notion of logical consequence, which says that B is logical consequence of AN, if under any interpretation that makes these, say, axioms true, it makes also B true, right? And that's interesting because logical rules, like model ponens, they are supposed to simply reflect this relation of logical consequence, which in a sense is the truth of the meta, right? So the concept of real under that conception becomes purely syntactic and kind of secondary. It's kind of Platonic picture. We have B is a consequence of all this A in kind of Platonic heaven. And then we making kind of little tricks with symbols to express this and not fully express it because of Gödel's first incompleteness, right? But somehow express, right? So that concept of real simply is completely technical. And this notion of consequence, logical consequence, it doesn't have epistemic aspect any. It's supposed to be simply truth in the strong sense of being absolutely independent of any epistemic attitude, any knowledge about that, right? So that question that inference somehow is instrument of knowledge, instrument of proof, does not arise here, right? So it's somehow compatible. For example, we may assume that Fermat-Gray theorem is a logical consequence of Zermelo-Frankel axioms plus some countenance or something, right? And that theory does not allow us to say why it's not complete proof. So it doesn't allow us to distinguish between consequences which are kind of self-evident, right, and those which are not. That's completely different epistemic issue. That's kind of purely ontological. Okay? Right, and what is alternative approach? Alternative approach has been dates back at least to Gensen. His first idea was somehow make more rules. He actually worked not with axiomatic theories like set theory or something, but with what Hilbert described as axiomatization of logic, which is basically a way to put some tautologies, one real model exponents, and generates all formula from this list of tautologies. And Gensen remarked that that could be some presentation of logical calculus, but it's not kind of presentation that is useful somehow, right? What we're looking, according to him, in logic is kind of system of rules. So his idea was to get rid of all axioms and replace them by rules. No, in a sense, of course, every axiom may be seen as a rule with empty premises, right? All right. But more generally, we have something above here too. But the important thing, how it's related to semantics, so he produced well-known natural deduction, second calculus, and he made this remark, which now is very often quoted, that introduction rules represent kind of definition of symbols. And that, of course, can be compared with Hilbert's idea that giving axioms, for example, for sets, we define sets in that way, right? Whatever satisfies the axioms, we would call set. And here he would say he defined logical connectives in that way. But I would like to stress the difference. There is this common background, but there is different. Because here he talked about rule, right? And when Hilbert talked about, or we talk about axioms, about propositions, rules are not propositions, right? It's something very different. So we have rules with operation with symbols, and these rules are supposed to somehow define what these symbols mean. And that basically idea of this procedural semantics, which is very different, right? Because to repeat this, Tarski semantic is also propositional. It's kind of meta proposition about all models, right? So we define consequence relation in terms of meta proposition. And here it's attempt to, to make rule itself to define something. Yeah, but by the way, even in literature, I think it's, when people talk about models of, say, Martin-Löf type theory, I think there is a lot of, I would not call it confusion, but mathematically people doing interesting things, but conceptually, for example, if we talk about interpreting rules, which is a rather common term, but what exactly it means? At least it's not Tarski's satisfaction relation, which only works with proposition, but rule is something different. So interpreting rule should mean something else. And then I would refer also to Doug Pravitz. He was not the first in this, but I think it's a good point in the 70s. So he argued that proof theory, in the sense of Hilbert, is not, how to say, correct. No, it is kind of a very specific aspect of what he would call general proof theory, right? Because you would say kind of a string of symbols which takes us from axioms to theorem can serve a proof, right? But there is more general notion of proof also in mathematics, and moreover outside mathematics, when I don't know, we use some material evidence as a proof, like in the court, for example, right? Why not? And still, according to him, we can make mathematical theory even about things like that. Roughly, here idea that we take proof as a primitive object, but then we show how from primitive proof construct more sophisticated proof. That's basic idea. And technically, Doug Pravitz and Per Martendorf, they are working very closely together, and they still together. It was in August. They made 2 talks. And they have some small disagreements, so they don't like if I say Martendorf realized Pravitz's ideas, but the agreements are really minor. I will not go to them. So Doug Pravitz is more like philosopher, right? So he suggested idea, and Per Martendorf is very, he's of course more mathematician. So I take Martendorf type theory as very much as a realization of this Doug Pravitz's ideas. And he has that paper on 85 called meaning. He introduced that notion meaning explanation, which is kind of supposed to replace what is model theory in Tarski's sense. And he the paper is called, I think, type theory and computer programming, something like that. So the idea basically that what provides semantics is kind of compiler, like compiler in computer. So it's not that you assign to symbols some entities, that's their meaning, right? And meaning, according to him, it's a kind of lower level program which interprets your program into something like into actions, into computer code. Well, actually, he also thought for like human, right? So we have this formal proof, and then we should interpret each symbols in a way that it makes in our brain kind of actions, and if it serves as proof, its action is such as it generates justified belief in our brain. That's the idea, right? No, and more recently, it was called this whole area proof theoretic semantics, which in the beginning was a little bit like a provocative title, right? Because it was supposed that proof theory is about syntax, like in Hilbert, and semantics is about models. And here, proof theoretic semantics, so it's kind of dialectical synthesis. But look, for example, in the beginning was supposed a rule should be supposed to be given such a way that everything derivable would qualify as a proof, all right, in that sense. But other people now suggest that should be some restrictions, so not everything derivable, but derivable with some conditions that make it into proof. So there is a lot of work going there. And I think interesting project I'm trying myself to think is that Gensen, he only talked about logic, and unlike Hilbert, right, who had this visionary thinking, axiomatized physics, and a lot of things, right, just Gensen only axiomatized logic, but I think it's really interesting project to apply this approach also more broadly, and in particular, say, knowledge representation more broadly. Yeah, what are advantages here that we really may manage proof different kinds, including like empirical proofs, right? So we using the simple proofs, we construct more complicated proofs, it allows also represent as knowledge how, because it's in the form of formal rules. And it is, as I put it, computer friendly because since those are rules, it's more, of course, more directly implementable into computer code. Now I have this part explaining basic things about univalent foundation. Maybe I should not. Maybe I can remain for question time and ask a question. So it's all based on syntax of Martin-Löf type theory. And actually, I would say even Volodya Voevodsky didn't like to say this. He wanted to really look at Martin-Löf type theory as a pure syntax. So he somehow, he was invited in August as a chair of talk of Doug Privates. And before the talk, he asked me, who is Doug Private? So he was not very much in these ideas. Right, but I think that as a matter of fact, no, at least as I see this, really this univalent foundation, this all this homotopical, really builds upon that work, which also on semantic level, not on syntactic level. And actually, it's very nicely clarifies certain issues in semantic of Martin-Löf, because in the beginning, for example, of his book, I think it's 84. 82. No, he lectured 82, but then it was published, 83, no, that's right, next year. So he was kind of very liberal about how to interpret types and terms. You say it could be, you could think about it as a set, an element, or as, meaning this Karikova corresponds as a proposition and proof, or as intention and fulfilling, and that's, I think, his interest to Husserl reflected here. Or after Kolmogorov as the method algorithm solving a problem. So type is a problem and a term is solution. So everything is okay somehow, right? Then even he somehow says if you think deeply, you understand that set and proposition is the same thing. So he gives some argument. But actually, this homotopical interpretation, it actually clarifies that. It's so if you take it seriously on semantic level, it just shows that not all types are sets, but sets of types of particular kinds called as H level, homotopical level, right? So it really shows which types are propositions, which types are sets. So it's no longer, you don't any longer need to confuse everything together. You see? Basically, propositions are types that have at most one element. So it's empty is false, or there is so there is also this idea that if you have any type, you may truncate it. Not geometrically, you may truncate it, and that means that you may be not interested what exactly is sitting there, but only in the fact that something is sitting there or nothing. Right? For example, theorem has a proof or has no proof, and you are not interested in distinguishing different proofs, so it's kind of first approximation, and that's exactly what we call proposition and truth, right? And if you go in more sophisticated way and distinguish between proofs, right? Then you need something more than proposition. But actually, what I described, it's kind of I don't know, at least epistemic way, it's different. It's the other way around, right? So to prove something, I need constructive proof, right? So I need to think about, not only about proposition, to prove it. Right. No, so my suggestion, I think it's maybe very nicely work as at least this philosophical, conceptual background for knowledge representation, and that was one of also Vladimir's ideas to apply it more broadly, this approach. How to make it technically exactly, I don't know, but that's no. So the conclusion, I think, again, they were looking in this foundation mathematics of their time, and that was quite natural thing to do, but I think today we may revise these ideas, and basically if we kind of trying to do the same thing these people were doing 50 years ago, right? Rather than just follow their foundation, we may rather revise it once again. Okay, thank you. Okay, thank you. No, a little bit. Okay, let's have some questions.
I have a little technical remark. And Martin type theory.
Yeah, put your mic.
Martin Love type theory, as any system of type lambda calculus, should have trivial axiom. Well, you wrote that no axioms, but there should be trivial axiom from x of type A implies that x of type A, so that should be end of proof 3, you know. So that's trivial axiom because we need to finish our proof 3. Well, that's the single axiom in the system of in the system of type lambda calculus, as in natural deduction or sequent calculus. So technically, we have one axiom in Martin Love type theory, as in proof theory in general. Well, that's a little technical remark.
Yeah, probably one thing was my slide, but somehow I missed, that idea of Pravets of all these people was somehow epistemic also. So of course, motivation for constructive logic is avoid talking about truth without proof, right? While in this classical case, exactly was opposite motivation, that we should well distinguish proof and truth, and somehow logic should be about truth and not about proof. No, at least first we should take care about truth and then about proof next, and about knowledge, all right? And that's really two different approaches, because I think at least some kind of approaches in epistemic logic is just we have this logic of truth, so to speak, right? And we add some, say, modality. We explain now, next step, we explain what it amounts to know certain truth, right? And here approach is different. It's rather, the idea is that in some instances you may find that they really confuse truth and proof. They would say, okay, we call something true if there is a proof. Right. Anyway, here is idea is somehow introduced, making logic epistemic to begin with. And I think it's very interesting how we may, I don't know, compare, balance these two approaches. Okay. Сергей. Ты знаешь, мы, поскольку на другом копии, потому что мы сейчас maybe 5 minutes.
Костя слег. Он был.
Да, он мне написал.
So, dear colleagues, my name is Sergey Kovalёv. In our project, I in our project, my part concerns various engineering applications of knowledge management. So today I will present a brief overview of knowledge management approaches in the field of digital design of novel materials. The scientific basis for digital design of materials is called computational materials science. The computational models of materials are usually arranged according to the scale of length. For example, starting from electronic levels at nanometers and smaller scales, then atomistic models, then microstructure, and finally macroscale. Sometimes between microstructure and microscales, sometimes the intermediate scale of modeling, so-called mesoscale, is introduced to represent, for example, composite materials. There are a number of scientific centers that gather, collect the knowledge useful for digital design of materials. Such centers exist in the United States, Europe, Japan, and even in Russia. The methods to synthesize materials are very different. For example, in this slide, I show some methods which are usually attributed as considered as traditional, meaning that they are basically known for many thousands of years, and innovative, meaning that they usually require technologies that are available, that started to be available only recently. So the traditional methods include smelting, weaving, electrolysis, and some others. As innovative, we consider, for example, vapor deposition in plasma, three-dimensional printing, or even viral assembly, where the genetically programmed viruses compose the nanostructure of materials. There are such experiments, for example, in MIT. Naturally, innovative methods to design materials require innovative mathematical models and informational models of products, processes, and materials. As an example, here the so-called functional voxel approach to modeling, the materials modeling is presented. It is useful for additive manufacturing materials. It is based on geometric modeling of constructions in space, uniformly partitioned into discrete point elements called voxels, which is acronym for volumetric pixels. Basically, the voxel representation is known for several decades, but it weren't used in the mainstream engineering software tools until recently, when it was realized that this approach is natural to represent to directly represent the structure of material which is created by three-dimensional printing. That is, the 3D printing essentially produces material produces construct specifically voxel by voxel. So it is possible to directly compute multi-physical effects on each voxel. This is the example here is taken from a university textbook on elasticity theory, where the balance of elastic forces on a small volume of construction is computed. And as you may remember from the university course, then the limit transition is taken to when the volume of the piece goes to zero, approaches zero, and the balance of forces produce the differential equation, the partial differential equation that describes the elastic body in terms of essentially mathematical physics. When we, in computer methods, we usually go then to back to discretize these differential equations, this differential equation, and apply various numerical and mathematical methods. Voxel approach allows to skip these two pieces, go into differential equation and back to its discretizing, and instead directly, as I said, directly compute multi-physical effects on each voxel. This is computationally difficult, but easily parallelizable, as it can be seen. So now let me overview some other approaches of computational analysis of materials. Here the geometric analysis is represented. One example is based on differential geometry, where we compute the layout of textile composite based on the fact that specific weaves are usually go along geodesic lines of the form of construct. And another more, somehow more advanced approach is based on applying algebraic geometry and topology. For example, consider a conjecture that nuclear power production is a homotopy invariant of nuclear reactor construction. Indeed, as shown by Feynman, the two quantum particles are identical exactly when their trajectories are homotopic. And so we can influence the behavior of particles by introducing some non-trivial topology, which forces different particles to go along non-homotopic trajectories, and thus exhibiting various effects such as forces and interaction. This is basically what topological quantum field theory is about. And for example, here is an example where we insert a control rod into the mass of nuclear fuel. Then essentially we introduce non-trivial topology. We increase the topological genus of the piece. And so this essentially leads to controllable nuclear power production.
What is meant production is homotopy invariant? So it's like all reactors are homotopically equivalent?
No. I mean that in this, of course, this is more well, conceptual level conjecture. It states that when we have two topologies of nuclear fuel core are homotopic to each other, then we have the basically the same or differ from scale the production. And when we introduce well different, or rather different topological structure, which are homotopically different topological structures of piece of fuel, produce different different capacity, energetic capacity of reactors. And so, and indeed, there is a number of research to form different topologies, different geometry of nuclear fuel pieces to produce different capacities and essentially different behavior of the nuclear reaction. Another very well-known method of computational analysis of material is so-called finite element method. It's specifically the basic, the canonical method of discretizing the differential equations of mathematical physics, such as elastic theory, thermodynamics, electrodynamics, etc. And here is an example of a number of computational tools that are used for composite materials. As an alternative to finite element analysis, various methods called mesh-free are under development now, which are based on constructing various computational models that directly represent the most important structural characteristics of the material under analysis and produce the tailored computational models that reflect this structure. The functional voxel model introduced above is an example of such approach, and there are another mesh-free methods such as material particle method, for example, used for nanocomposites. Statistical approaches. There is a big number of statistical approaches on different scale. For example, the ab initio quantum level modeling, where we essentially we model the production of materials on a computer at electronic and atomistic levels by direct, essentially by solving quantum mechanics equations with various statistical averaging, such as density functional and some other computational quantum mechanics techniques that allow to evaluate the integrated physical characteristics of materials starting from their assembling in electronic and atomistic level. And another example of this approach is Monte Carlo simulation, which is useful for kinetic models of materials, for example. Homogenization is a method that there is a number of methods that allow computing the integrated characteristics of heterogeneous materials that characterize their behavior as if they are homogenic. For example, for laminated layered composites, it is possible to evaluate effective Young modulus and other elasticity characteristics in case when the such characteristics of particular layers are known and the geometry, that is the thickness of layers, are also known. And there is an interesting approach to homogenization that is based on category theory, when the characteristics and the structure of the material is represented as a certain kind of category theoretic diagrams in a category that represent the information known about the layers and the structure of the material, and the relationships that allow to derive effective characteristics are occur as requirements for certain diagrams to be commutative, when we in a sense when we follow different paths in the diagram and require that they produce the same result, we have the balancing equations, such as similar to those which are known in classical layer eliminate model. Also under active development now are the neural network analysis. They are useful methods. Such approach is useful in cases where we don't know the specific physical model or of certain situation, and we don't know the exact number of laws and physical laws, constants, and effects that lead to certain behavior of material. But we have a number of experimental results, dependencies of the characteristics of material on, for example, the structure or on external conditions, etc. And we approximate these experimental results by training the neural network. And since it is known that neural networks are in certain sense universal approximator, then we produce results which generally coincide with experiments. This kind of analysis doesn't explain why the material behaves exactly as we see, but it allows to it produces rather relevant guesses about how it behaves in specific cases where we don't have direct experimental values. It allows to fill gaps between experimental values, experimental data, and it is as shown here as an example. Naturally, all the methods outlined above have their strengths and their weaknesses, and that is to say, their specific areas of applications, and these areas are overlapping, but no method can dominate others and can be considered, is reasonable to be considered as universal and the one better than others. So the multivariate approach is useful when the various specific models, specific methods, and tools that implement these methods are placed over the common knowledge management base and under the control module that drives the processes of modeling and optimization of materials. And this module is in turn supervised by the user interaction when the user states the initial problem and the initial conditions and receives the results of modeling and optimization. That is the recommendations for example, for optimal structure of material or for optimal technological process of produce the specific construction. With such multivariate approach essentially opens new horizons in digital design of novel materials and in material science in general. Thank you for your attention. Questions, please. No questions, okay.
No. So what you described, or if I understood correctly, was basically different ways of modeling materials.
Right, and representing relevant knowledge. That's right.
Yeah, but could you probably, because the second part I understood less. So I understood that you may mathematically model materials in all these different ways.
Yes.
And combine them, but how they, could you probably just repeat this moment of representation of knowledge, how this is represented and used?
Essentially, indeed, different ways of modeling materials imply different, or maybe are based on different ways of represent existing knowledge about materials. For example, let's see that, for example, finite element method is based on representation of knowledge about behavior of materials based on mathematical physics, since it is basically the method of solving the partial differential equations, such as elasticity equations, elasticity theory, thermodynamics, electrodynamics, etc. The mesh-free methods are based on producing the specific tailored computational models based on the micro and mesostructure of materials. That is.
But could you actually, a little bit different question, how it's used? Could you explain? Maybe it's just going without saying. I mean, so we have, I don't know, computers, some storage, and these things are stored. So could you just give example maybe how it's used by, you manufacturer or
okay. For example, we assume that we design the new vessel, for example, and we want its hull to be made of composite material, for example, they say glass plastic, and we want this the hull to be the most hard, resistant to external condition, and at the same time the most the least expensive in production, and so we consider we generate different variants of structure of this our hull, various with different number of layers of materials, with different kinds of layers, and compute the various characteristics both of the result and the process via different methods, and use results of different methods to verificate each other for mutual verification, and then we compare the computed resulting characteristics of the material given by different conditions, and choose the one which best suits our technological and technical requirements.
Okay. So it's basically for engineering.
Yeah, this is the engineering that in past times all these were performed by real world natural experiments. We produced samples of different materials and tested them by applying various physical conditions and measuring their response. Now all this can be performed virtually in computers, and that's the advantage.
Okay, great. Well, maybe it's sort of a fantastic question, but what about a sort of predictive power of this formalism? So could it maybe propose some new ideas for designing materials which are not known yet? Not only for describing existing ones, but also for, say...
Currently, many people think that big predictive potential is associated with neural network analysis specifically, since big enough neural networks can go way outside, beyond their trained data, and essentially recommend to combine combine data in entirely different ways than these on which upon which they were trained. So essentially, but of course, the wild guesses produced by neural networks require verification by other methods, and so the predictive, as you say, predictive machinery in a multivariate approach can go from neural network predictive engines to other traditional methods and verification tools that allow to sort out the irrelevant predictions and essentially produce those which are valid.
Okay. Thank you.
Thank you.
let us resume. So now we invite Tudor Протопопеску, who will talk on intuitionistic epistemic logic.
Well, thank you very much for having me. It's nice to know that there's a project that is so close to this. Okay, so this is joint work with Sergei Artyomov, and the basic goal of the project was to give a view of knowledge which is based on the Brouwer-Haitink-Kolmogorov semantics, or intuitionistic logic. So the idea is to incorporate knowledge into an intuitionistic framework, specifically a BHK framework. And the other goal was to sort of incorporate the intuitive idea that knowledge is a product of verification. And I'll say a little bit about what that means. So there are two basic assumptions in building up an intuitionistic version of knowledge. The first is just the BHK semantics. The proposition is true if proved. And the idea that knowledge is the result of verification, which means some kind of evidence which is not necessarily an explicit proof. Right? And sort of from these two basic assumptions, we build up the rest. Right? The key idea is that a verification need not be a proof. Right? And this is just based on the idea that we often claim to know things on the basis of evidence which we don't consider to be proof in the full-fledged sense. Right? Weaker or more general evidence is often thought to be good enough. Right? So it's trying to capture this intuitive idea. Okay, and the overall picture of how intuitionistic knowledge works as opposed to classical knowledge. So when I say classical knowledge, think here knowledge as described by a system like S4 or S5 or something like that. So knowledge on top of classical logic. So in the classical universe, knowledge implies truth. Knowledge is something stronger than truth, right? You have to do more, or you have to, there's more to knowledge than simply the truth of the proposition. And in the intuitionistic universe, sort of the converse holds. There's truth yields knowledge. And we'll see how that works. That may be surprising at first, but it shouldn't be really. Intuitionistic truth is based on proof. Well, if you have a proof, then you know something. I mean, that's the sort of the core idea. All right, so the Brouwer-Haitink-Kolmogorov semantics, right? A proposition is true if there's a proof of it, false if we can show that the assumption that there is a proof leads to a contradiction, and then this gets extended to the logical connectives in a way which I assume is familiar to all of you. Of course, the important one is the one for implication. A proof of an implication is the construction which, given a proof of the antecedent, gives you a proof of the consequent, right? It shows you how to turn a proof of A into a proof of B, and negation is just an abbreviation for implication to falsum. Okay, and what we want to do is add knowledge to this framework, right? So we want to interpret the idea of knowledge within this. Okay, and the basic idea is knowledge is the result of verification, where verification is just some kind of evidence or some kind of procedure which is considered sufficiently conclusive to warrant a claim to knowledge. Right? If you do this, you can say, I know this, and reasonable people would accept that, but it's not necessarily a proof. So the formal definition for BHK, for adding knowledge into the BHK framework, is that a proof of A is known is a proof of a verification that A has a proof. Right? And you can read this as saying that a verification of A is something which contains enough information to conclude that there is a proof of A without necessarily delivering that proof. Right? You have sufficient guarantee that the proof is out there in some sense. And here's an example, and I'm very happy that you mentioned this earlier in your talk, because an example is a truncated type in intuitionistic type theory. Right? So a proposition, a proposition type in intuitionistic type theory, right? We can think of them as sort of sets whose elements are proofs of the proposition in question. Given a proposition type A, you can form a truncated type, right? Which has at most one inhabitant and basically just conveys the information that the type A has inhabitants, right? So it says yes if there's a proof, it says no if there's no proof, and that's all, right? So this is an example of something which tells you that a proof in some sense exists, but doesn't necessarily deliver the specific inhabitant of type A, right? So we can interpret Ka as this int K. I believe this is from the homotopy type theory book. So truncated types are also called squash types or monotypes. But anyway, so this is one example of how intuitionistic knowledge can do this. Give you a guarantee that a proof exists without necessarily delivering that proof. Okay, and how do we read a formula of the type Ka? What does it say? Well, they can be different readings depending on what you think of this issue of whether you need to be aware of the existence of a proof or not. So the traditional understanding in intuitionistic philosophy of mathematics, so Heiting and Brouwer, is that a proposition is true. You have a proof when, when indeed you have constructed that proof and you're aware of this proof, right? So Heiting says that in the study of mental mathematical construction, so when you do mathematics, to exist is the same thing as to be constructed, right? So a proposition is true when you have the proof in hand. But there's also a sort of another strand of intuitionistic thought from Pravitz and Martin Löf, who think of proofs as Platonic entities. And truth is sort of cashed out as the existence of this proof, and knowledge is relative to that. So you can have two different readings of knowledge, of BHK knowledge. If you take the more traditional view, A is known, so Ka can be read as A is known in the more traditional sense, like you have the verification in your pocket. On the Pravitz-Martin Löf line, you can understand it as saying that A can be known under appropriate conditions. Okay, and so what follows from this sort of basic assumption about how knowledge works? Well, the first is that the co-reflection principle, A implies that A is known, is valid intuitionistically, right? So why is this? Well, consider that on the BHK reading of co-reflection, it says that given a proof of A, you can construct a proof that A is known, right? And can you always do this? Well, yes, you can do this because first, proofs are checkable. So if you have a proof, you can obtain a proof that you have a proof. But also, proofs are kinds of verifications. So if you have a proof that you have a proof, you have a proof that you have a verification, right? So this is, so what follows from this is that, well, this is not only valid, but in a sense, this is basic for any kind of view which incorporates knowledge into an intuitionistic framework, right? So we're not the first to propose that this is valid intuitionistically, but as far as I know, we were the first to propose that intuitionists should take this seriously, that this is in fact foundational for an intuitionistic view of knowledge. And the second thing that follows from the definition of how knowledge works is that the reflection principle is not intuitionistically valid, which may be surprising, and certainly some people find it surprising. Because consider that on a BHK reading, it says that given a proof of Ka, you can always construct the proof of A, right? And I mean, just by assumption, the idea is that you can have Ka without necessarily having the proof of A. So you may not be in a position to extract the specific proof of A from the fact that you have a verification. Okay, so reflection is not necessarily valid. So some examples, and also some other examples of intuitionistic knowledge. So for instance, zero knowledge protocols are ones where the reflection principle doesn't necessarily hold, because by design they're supposed to convince the verifier that you know something, right, or that a statement is true, without actually delivering the proof, or you convince your bank that you're the person you say you are without telling them your password, or them having the password in hand, or something of that sort. Another example, testimony by authority. So if take Fermat's last theorem, right? You may well be in a position to claim to know that Fermat's last theorem is true, but you can't deliver the proof, right? I mean, I'm certainly not in a position to do that. I take it, it's very complex. But if you're sufficiently educated so that you really understand the content of what the theorem says, then from the fact that people really have done the proof and they've said, yes, this really is correct, well, it's legitimate to claim that you know that it's true. Okay, I mean, that's another possible example. A yet third example, and this is my personal favorite. So somebody stole your wallet in the subway. You definitely know that there exists an X such that X stole your wallet, right? You have all the evidence you could wish for that, but from this you can't necessarily conclude intuitionistically, of course, that there exists an X such that X stole your wallet, because for that you would need to have a witness for the X, that is, a specific person, and you would have to have a proof that they're the ones who stole your wallet. So you can know somebody took it without knowing who did it and being able to prove that they're the ones who did it. All right, so these are all examples of the failure of reflection. So the moral is that reflection is just too strong in an intuitionistic context. Okay, but the problem is that reflection is considered to be absolutely basic for knowledge. I mean, if there's any principle of knowledge which is valid, then it has to be this one. And this is maybe also especially puzzling from a constructive standpoint, because other people who have constructed intuitionistic epistemic logics, so for instance, Timothy Williamson and Proietti, I've forgotten his first name, both explicitly argue for the validity of this within an intuitionistic framework. Right? They insist that this must be the case, and even more generally, Crispin Wright insists that if you don't have reflection in a theory of knowledge, then you're just not talking about knowledge. You're talking about something else. And it's sort of easy enough to see why you would think this, right? The reflection principle is supposed to express what's known as the truth condition on knowledge, right? You can only know true propositions, or, stated another way, false propositions cannot be known. The thing is that when you're talking classically, saying that only true propositions can be known and that false propositions cannot be known are equivalent. In an intuitionistic framework, these are not equivalent ways of stating the truth condition. So when you go intuitionistic, you have to distinguish between saying only true propositions can be known and false propositions cannot be known. And that's the proposal for how to incorporate the truth condition into an intuitionistic framework, right? So how do we say that false propositions cannot be known? Well, here are various intuitionistic ways in which you can say that. Now, so you might say, for instance, it's not the case that A is known and false, or if A is false, then it's not known, and so forth. Now, the thing to notice is that 1 through to 4 are all classically equivalent to reflection, right? And this is just given, in a classical semantics, all truths
Are they equivalent between them intuitionistically?
So, yes, they are. So they're all, given co-reflection, they're all equivalent intuitionistically. And they're all strictly weaker intuitionistically than reflection. So reflection is just, it's too strong, right? It says more than you want to say, certainly in an intuitionistic framework, maybe even in a classical framework. I mean, that's a different topic, but still. So how should one express the truth condition? Because of course, we don't want it to be the case that we can know false propositions. Well, the argument, well, we suggest, well, any of these will do. Since they're equivalent, you can formulate the truth condition with any of these. Our proposal is that this is, in some sense, the clearest one. One, it has the same form as reflection, and that's nice. And it just has a direct reading saying that if A is known, then it's impossible for it to be false. So, you know, it states quite directly the truth condition. And, well, it's equivalent classically, in a classical logic, it's equivalent to reflection. But another reason for it, for incorporating this, is due to the double negation translation and of classical logic into intuitionistic logic and Glivenko's theorem. Right, so Glivenko's theorem says that if you can prove something in classical propositional logic, then the double negation is intuitionistically provable. And you can read this informally as a double negation, as saying, as a way for the intuitionist to express the idea that A is classically true. Right? So true without a specific witness. The double negation intuitionistically is a way of saying that the proposition is true without necessarily having the proof in hand. Right? So the nice thing about intuitionistic reflection is that it says the same thing as what the reflection principle says interpreted classically. It's true, right? Where by true we just mean true without a specific witness. Right? We just care that there is some kind of proof somewhere, maybe who knows where, but we don't necessarily have to have it in hand. Okay, and so the overall picture then is that intuitionistic truth yields intuitionistic knowledge, verification, and verification in turn yields classical truth. Right? If you take on board, so formally we can prove this, and if you take the idea that double negation is a way of saying classical truth, then sort of this is the overall picture of where intuitionistic knowledge fits in the universe of intuitionistic versus classical truth. Okay, so given all this, we can define a system of intuitionistic epistemic logic, and so we take intuitionistic logic, propositional intuitionistic logic, the distribution axiom, co-reflection, and intuitionistic reflection. And that's it, right? So this is the basic logic of intuitionistic knowledge. The only rule is modus ponens, and we can prove some nice things about it. So necessitation is derivable. Of course, from co-reflection, the rule follows easy. Deduction theorem, uniform substitution, and notice that the kind of knowledge we're talking about is sort of S5 in some sense, because positive introspection and negative introspection are derivable. They're just instances of co-reflection, right? Okay, so it's a very robust sense of knowledge. Now we can also, if you take the idea that the difference between belief and knowledge is that belief does not need to satisfy the truth condition, then if you drop intuitionistic reflection and you get the system IEL minus, then you get the system of intuitionistic belief, right? Beliefs which could be false. Okay, and if you add any of these possible ways of expressing the truth condition to IEL minus, you get a system which is equivalent to IEL. So all of these work. And then also in IEL, we can prove that all of these are equivalent to this. That's easy to do. And notice that we can also embed classical epistemic logic into IEL, but not faithfully, right? So it's easy enough to show that the double negation of, so take the classical logic S5, and then any of the belief logics, KD, KD4, KD4, 5, any theorem of these logics, the double negation of any of these theorems is provable in IEL, but it's not necessarily the case that the double negation of some IEL theorem is provable in any of these classical logics, namely this one, right? So what this means is that IEL is in a sense more general as a logic of knowledge than classical logic. So you can do all of the classical reasoning that you might want to do within IEL and then do some other stuff also. So, I mean, that's sort of interesting, that everything that is, you may consider correct or correctly expressed by a logic of knowledge like S5 is preserved within IEL, right? So another thing this means is that giving up reflection really doesn't mean giving up anything that the classical epistemologist might want, which is sort of interesting. And one sort of limitation of the IEL framework is that as far as the language is concerned, knowledge is just provably consistent belief, right? So we could formulate IEL, a logic of knowledge, as IEL minus with this, which just says knowledge is provably consistent. It's just consistency. Does this mean that intuitionistic knowledge is just provable consistency? Well, no, not necessarily. It just means that IEL doesn't have the expressive resources to distinguish between provable consistency and knowledge, well, and to distinguish between these. Okay, that's a limitation of the language, but it's the same kind of limitation you have in the classical universe where, for instance, knowledge is just true belief, a certain kind of true belief, right? If you want to distinguish between knowledge and true belief classically, well, you need something else. Right? You have to incorporate more into your language, or it's like justification logic, doing that. Okay, and there's an analogous sort of limitation in the intuitionistic part. Okay, and there are models, right? Everybody loves Kripke models for epistemic modeling, and IEL has Kripke models. All right, so we take an ordinary intuitionistic Kripke model that is WR and forcing, and we add an extra accessibility relation. So you can think of regular Kripke models as modeling sort of the logical possibilities of an agent proving various propositions, and then this extra accessibility relation is modeling possible verifications. Not proofs, but ways verifications might go. Okay, and so R is, of course, transitive and reflexive, or it's a partial order, and E has to be non-empty, right? Every state has some state E accessible from it. E is a subset of the R relation, and then we have this condition which says that if you can take an R step and then an E step, you can get there in an E step in the first place. And this gives you the soundness of intuitionistic reflection. The third one gives you monotonicity, and this gives you co-reflection. Okay, and then knowledge is just, right, Ka holds at a state if A is true at all E accessible states. So it's an intuitionistic modal logic with knowledge behaving in just the way that knowledge behaves in classical Kripke models. Monotonicity holds in general, so if A holds at a state, then A holds at any accessible state, any R accessible state. I won't go through the proof. IEL is sound and complete with respect to these models. Of course, reflection doesn't hold, and here's a nice little example of an intuitionistic model, intuitionistic epistemic model, right? So we have two states, and right, E, state 2 is E accessible from 1, and of course, because we have seriality, 2 has to be accessible from itself. P holds at 2, it doesn't hold at 1, so P is known at 1, but of course P is not true at 1. Right? So at the state 1, reflection doesn't hold. Okay. Some other interesting properties. Reflection holds for negative formulas, and the reflection rule is admissible. And knowledge and negation commute. You might read this as saying that the impossibility of verifying something is equivalent to verifying that it could not possibly hold. We can also show that not knowing is equivalent to not being true or impossible to prove. We can also prove that, well, this, which you might read as saying that no truth is unverifiable or that all truths are knowable, right? It's not possible to be, it's not possible to not possibly verify A or to not possibly verify not A. Impossible, that is. Intuitionistic verifications don't have the disjunction property in this strong form, which, you know, sort of makes sense given that something like KA is more classical than intuitionistic. Right? So you might, this may not be so surprising. Here's a model which I guess we could discuss it later if you like. But we do have the disjunction property in general, and we have this weaker version of the disjunction property for knowledge. So if it's provable that A or B is known, then it's provable, then either KA or KB are provable. And that's just a corollary of the disjunction property in general. Okay, and IEL, this framework gives us a very nice way of solving, or in my view, solving a problem that is supposed to be totally devastating for intuitionistic views of truth and knowledge. So there's a paradox known as the knowability paradox, which is supposed to show that the whole idea of intuitionism is just wrong. It can't possibly work, right? So the idea is that, okay, if we try to generalize the idea of constructive truth from mathematics and sort of apply it more generally, what we get is the idea that the truth of a proposition is given by the conditions under which it's verified. And if that's the case, then it seems it's a small step to say that what's characteristic of constructive truth is that it is knowable, right? In order for a proposition to be true constructively, it has to be possible to know. This is the epistemic view of truth. Okay, so the slogan is all truths are knowable. And the argument goes that this is a way to formalize this notion. And you can see this is a direct translation, right? If F is true, then it's possible to know it. So this is supposed to be characteristic of constructive truth in some sense. Okay. And the knowability paradox shows, supposedly, that from this formula, we can derive this formula. And the weird thing about this formula is that it says if F is true, then F is known, and that says that all truths are known. So the knowability paradox shows that all truths are knowable implies that all truths are known. Right? And this is supposed to be a reductio ad absurdum of the whole notion of constructive truth. And this is due to Church and Fitch. So Church came up with the proof, but Fitch published it, and you know, the story is that he attributed it to an anonymous referee, which was later found out to be church. Are you familiar with this proof? Is it worth going through? Okay, so the idea is this, right? So we want to show that from this we can get to this. Okay. The key idea is that for F we take the formula P and not KP.
But what is set up? We have like two modalities.
Well, we have the K has to be at least T. That's actually all you need. So you need the K has to be reflexive, so T at least, and you need this. So any logic that has these. So I guess a K for the box, K, K system K, and T for knowledge. So for F, for F here, take P is true but not known. Okay, so this is just an instance of this knowability principle. And now, for the sake of deriving a contradiction, assume that it's known that P is true and not known. Okay, well, we can derive a contradiction from this pretty easily, right? We distribute the K, and then by reflection, the reflection principle from K not KP, we get not KP. Okay, and this is a contradiction, so it's not the case that it's known that P is true and not known. And then this is just the necessitation of 5. And then box not implies not diamond. So it's not possible to know P and not KP. And then from 7 and 1, right, we derive that it's not the case that P is true and not known. And then by some propositional reasoning, P implies not KP, eliminate the double negation, and you get P implies KP. Okay. Okay, so this is the Church-Fitch knowability paradox. Okay, so the argument goes that this shows, this proof, right? I mean, the proof is just a formal object, that all truths are knowable implies all truths are known. If that's true, then that's bad for intuitionism. So all of the intuitionistic responses to this proof have said that, well, we have to reject this, right? Because that's just crazy. Right? We don't know all truths. Okay, I think you can guess what the IEL response is. It's simply that this is a bogus problem. This is a pseudo problem. Because there's this whole way of setting up the problem only makes sense when you interpret things classically. When you really approach, say, this proof from an intuitionistic perspective, and you approach knowledge from an intuitionistic perspective, so when you talk about this formula, there's just no problem, right? So specifically, the knowability paradox depends on these assumptions. First, that this means all truths are known, and that this means that all truths are knowable, and third, that all truths are knowable is what is definitive or characteristic of intuitionistic truth. And from the IEL perspective, none of these are true. Right? So this is why the whole problem is bogus. So first, well, I mean, we've already been through this. This doesn't say that all truths are known. It says that proofs yield verifications. Right? And these are two very different statements. And in particular, all truths are known, right, only makes sense when you take A as reading it classically, right? When you read A intuitionistically, it says there's a proof of A, right? You've constructed a proof of A. And as we saw on the BHK reading, when you've constructed a proof of A, then it's just trivial, almost trivial, to claim that you know A. Okay, so first, right, well, intuitionistically, it doesn't say all truths are known. Okay, second, this is not a good way of expressing what is characteristic of intuitionistic truth in a classical language. So now, suppose that you want to work in a classical language and you want to talk about constructive truth. Okay, you can do that. Is this a good way of doing it? No, right? Because in a classical language, this says all classical truths are knowable, right? If A is classically true, then it's possible to know it, which is just false. And it's false it's just obviously false, right? The idea of classical truth is that it's not epistemic, right? It's just in this, what you were talking about, it's just out there, and it doesn't depend on the state of knowledge or the possibility of knowledge of anybody. Okay, and you know, if you're familiar with Gödel's translation of intuitionistic logic into S4, well, we know that there's a good way of talking about intuitionistic truth in a classical framework, right? You have to add something to add syntactically, right? You put a box in front of it, right? And you read it as provable. So inspired by this idea of Gödel's translation of IPC into S4, the way to say in a classical language that all truths are knowable is to say that if A is provable, if A is constructively true, then it's possible to know it. Yeah, okay, and that makes sense, right? So again, we reject this also. And third, look, the characteristic feature of intuitionistic truth is not that truth is knowable, it's that it's constructive, right? That you require a specific witness to claim the truth of A, and it's arguable that the co-reflection principle is a way of representing this, right? When you have a specific witness of A, well then you can claim to know A, because you've already built the proof, you have it in hand, right? So truth is knowable because it's constructive, it's not constructive because it's knowable. And if you want to say that all truths are knowable, well, here are two possible ways to express things, right? We saw this one before, and this also is another way of claiming that all truths are knowable, and both of them are very easy and immediate consequences of the constructivity of truth, which is just what you would expect. And that's it.
Questions?
And what about the first order counterparts? Are they developed for these systems?
No, not yet. It's one of those projects that's sort of sitting on my desk.
Yeah, because I thought about it when you noticed, well, that A implies KA implies not A,
yeah.
And not A is referred as classical truth, which is due to Glivenka. Which is due to Glivenka, absolutely okay in the propositional case, but for first order we don't have Glivenka.
Right.
And this could just give some extra problems.
Right, yes, this is...
So this could be one issue that I just...
Yeah.
And that made me think about the first order problem. And the second question is about justification logic in this setting. So we know that in systems where we talk about some basically modalities that mean something like being verifiable, provable, something like that, we have model logics, and then we have the justification counterpart with explicit knowledge. Is it supposed to be developed here also for this K modality or for the intuitionistic thing?
Well, there are Roman Kuznets and some of his collaborators have developed intuitionistic justification logics. Right? So the justification logics take classical modal logics, the well-known ones, classical like S4, S5, S4, the big one, and you get a justification counterpart. But these are classical logics, right? To get a justification logic for something like IEL, you need a justification logic for an intuitionistic model logic, right? And you've done some work on this. I haven't applied it yet to another sort of way of looking at intuitionistic epistemic logic. So there's, you can translate intuitionistic epistemic logic into an extension of S4. So intuitionistic logic goes into S4, and then you add another modality to classical S4. And there's a system of justification logic with an extra modality for verification, where you have explicit proofs for the intuitionistic truth, right? So the logic of proofs, basically, with a verification modality added. So there's also...
So is it sort of a bi-justification logic? So do you have two sorts of justification terms, one for proof and the other for knowledge?
No, but you could do it that way also.
So in the system you are talking about now, is it right that you have a transparent system for intuitionistic part and sort of an opaque system for so just K, which is not a justified thing?
Yes, yes. But it shouldn't. Again, this is another thing just sort of sitting on my desk. It shouldn't be too hard to have a transparency for both parts. So we have the logic of proofs for the intuitionistic part, and then something weaker for the verification part. Indeed, it would be the justification counterpart for verification for the classical translation of the K modality would be the system D. Right? So that's the justification system K. J. And putting the two together, I don't think should be especially difficult.
Well, maybe the also maybe harder thing could be something like arithmetical interpretations and stuff like that. For that. So.
Yes, sure.
Because this was one of the intended, say, semantics for LP basically and stuff like that.
Yes, and there's an arithmetical interpretation of intuitionistic epistemic logic as well. Right? So basically, you interpret the verification modality as a verification predicate in piano lit. So an example of a verification predicate is provability.
But not the unique example, so there are others.
No, there are others. Yeah.
So are, say, these Japaridze style modalities like provability with sigma k axioms added, or pi k axioms, are they examples of such verifications, or they do not satisfy something?
I'm not sure. Maybe. I haven't thought about it sufficiently to say one way or the other. But, I mean, there's provability is one example. Provability with the added statement that arithmetic is consistent, or provability with the added statement that arithmetic is inconsistent, extended systems, are all examples of possible verification predicates. Right? But these are all still, as it were, implicit or non-transparent. I like that word very much. Non-transparent examples, as opposed to the logic of proofs part, interpretation, to get a function or build. Question?
Hello. My name is Daniel. I'm a master student in logic in the Department of Philosophy in MSU, and I'm a Haskell developer in Slam Labs startup. Well, my report is about intuitionistic epistemic logic too, but with different motivation from computer science and functional programming. So my report will be more technical by this reason. Well, let's talk about motivation, and motivation will be a brief introduction into functional programming. Well, programming languages functional like Haskell, and Haskell-like languages like PureScript, Elm, or Idris. Haskell is pure functional programming based on lambda p omega type system with a polymorphic lambda calculus with kinds. Idris is dependently type extension of Haskell. PureScript and Elm are Haskell style languages for web development. We may divide the types in Haskell or PureScript or Elm or Idris into two parts: simple types or pure types or parameterized types. Idea of parameterized types lies within lambda calculus type lambda calculus with kinds. Well, it doesn't really matter. Simple types is basic types like integers, strings, characters, Unicode characters, double, unit, and something like that. So is a usual data type, as in the rest functional or imperative languages. Parameterized types like list of integers, maybe char, in-out string. These parameterized types are used for calculation with some side effect. Well, programs with input-output, partial defined functions, function with multiple values, or something like that. By the same way, we may divide functions into two parts: simple functions and parameterized functions, like integer from integer, strings from strings to integers, or stuff like that, and parameterized function from maybe int to input-output int or list.
Parameterized, is it the dependent types, just special case of parameterized types?
Yeah.
Okay.
Yeah, in lambda cube special case. Parameterized types like list of strings into list of integers or something like that. And we have type classes for work with parameterized functions. Well, it's a kind of holy trinity in functional programming: functors, monads, and applicative functors. So, we consider briefly functors and monads and applicative functors after that. So, type class functor is a general interface for uniform action of a parameterized type, generalization of the map function on lists. So, map function on lists is a higher order function which carry function from A to B through list of an object of type A. In other words, we have function and apply this function on every element of list. So functor is generalization, this operation on lists. Well, so it's looks like a functor in category theory. So according to package, a monad is the more strongest structure. It's from the perspective of a Haskell programmer, is the best to think of a model as an abstract data type for actions. So, action is a kind of, we have parameterized value and function which returns a parameterized value, and monad allows us to apply parameterized value to a function which returns parameterized value. So a sequence of actions is a monadic composition, also known as Claesley composition in category theory. So calculations in EO world is the special case of monadic calculations, so which looks very imperative. Well, you may watch for more details Haskell standard library. Well, applicative functor is stronger than functors but weaker than monads, similar to lax monoidal functors with additional natural transformation. Well, I think you understood why I'm talking about intuitionistic epistemic logic. Well, the first method, pure, is injects pure value of type A into a functor F. Star operator is a kind of application, so this operation carry application through functor F. Well, really not a difficult thing. Well, cases of uses, well, generalize of map for arbitrary sequence of embedded arguments into the functor, something like that. And more practical uses is parsing. For, well, Haskell programmers should say that applicative functor is used for context-free grammar parsing, but that's very conditionally. And type composition. By type composition, well, we have usual composition for functions, kind of J applied to X and apply F, but we may create the same operation on parameterized types. So applicative functor is a very convenient feature for type composition. Well, monadic calculations in theory. So monadic calculations are studied and described very well from the end of 80s or from the beginning of 90s. Well, the main result is monadic meta-language, Mogi meta-language, and some other articles. Well, you may read also some articles written by Valeria Depaiva about model type theory based on intuitionistic S4, where box denotes co-monad and diamond is a monad. Well, there is only 3 articles, but in the real world we have a very big number of these works about monadic calculations and model type theories for these topics. Well, applicative functors and in theory. Well, unfortunately, applicative functor is a known concept outside the community of Haskell developers or Haskellers. Possible reason, applicative functors are considered just from a programming point of view, without proof theoretical consideration, without semantics and some type system. Well, we have 2 articles by McBride and Rose Patterson. Well, applicative programming with effects. Well, that article is very well for programmers. It's about, okay guys, we have some production cases. For these cases we introduce this class, which is similar to some stuff in category theory. Well, that works very well for programmers, but that's not okay for logicians or for mathematicians. Well, but the second one article called Constructing Applicative Functors by Rose Patterson, well, that article has more mathematical approach, but however without a proof theoretical consideration, but Patterson described mathematically what is applicative functor, and I'm going to use that definition of applicative functor for model building. Well, but we need a good proof theory for that, and lambda calculus too. Well, it's convenient to solve such a problem using some intuitionistic model logic and building typed lambda calculus, which would be carry-forward isomorphic to this logic. Well, by this reason, we are going to use intuitionistic epistemic logic, IEL minus, which is intuitionistic logic of beliefs. Well, a couple of articles. The first one, intuitionistic epistemic logic by Sergei Titov and Tudor Протопопеску. The second one by Vladimir and Alexei Yatmanov is about proof theoretical approach for intuitionistic epistemic logic, and prove that IEL is P-space complete, as I remember right. Well, proof model type theory, so we should get the natural deduction for IEL minus and obtain model lambda calculus by proof assignment. So, in other words, we add to simple type theory the next type of rules for modality. So, if we don't watch on terms, then we get derivation rules for natural deduction, and really that's not hard to, well, let me write some stuff on this. Really that's not hard to check that if natural IEL minus proves A, then IEL minus proves A. So that's induction by derivation. We need to build Hilbert-style proofs. So that's not hard, but that's very boring.
What pure means?
Pure means is a type constructor for K modality. So I used notations from Haskell. Pure for first method, and this star for the second method.
So just name of method.
Yeah, name of methods. Well, name of methods are type constructors in our calculus. Well, some examples of derivation trees for correflection and for normality. So that's not rocket science, as I suppose. Well, substitution defined standardly and very naturally for pure and for star. So reduction. So in Haskell, any implementation of the applicative instance should preserve the next laws. Composition identity law that applicative functor should preserve identity function. Well, ID is lambda x dot x. Well, composition law is about applicative functor should preserve composition. Okay. Well, the third law, homomorphism law, so it talks about if we have two values embedded into functor by pure and application that star looks like homomorphism, we can make this thing. So, and interchange law that we may, if we know, I think that's really not hard. Well, in our system we set this law as reduction rules, special reduction rules, and additionally. So also we should have iter rules, iter reduction, but that's really not interesting. We will not consider that during this report. Well, we have some metaphorical properties. So that's non-interesting part. Basic lemmas for context about generation, about weakening, or something like that. Well, that's proved induction by derivation by very standard way. Subject reduction, well, that's more interesting property. So if we have derivable type declaration, and we know that subject of type declaration reduces to another term, that result of reduction is derivable too. So from computational point of view, it means that beta reduction preserve types. From proof theoretical reduction, we have a kind of proof transformation called proof normalization. No? Well, we may consider the case with homomorphism law. So if we have this guy, then we have this guy. So it's not hard to see by these derivation trees. Well, we need to continue. Well, and the most important part is about Church-Russell property, confluence in other words, and strong normalization. So that's really long to prove that, but strong normalization, or in other words, that any sequence of reduction terminates, we need to prove that by modifying and applying William Tate's method of logical relation. You may read about this method in Benjamin Peirce's book called Types and Programming Languages. So the second one is confluence, Church-Russell property. Well, we may prove that by checking local confluence. Well, simple confluence described for multi-step beta reduction, but local confluence is a weak diamond property. So that's a weak Church-Russell property. So we have here one-step reduction, not multi-step. So and apply Newman lemma. Do I need to explain what is Newman lemma? Well, I think I don't need that. So Newman lemma is about if relation is locally confluent and strongly normalizable, then it's confluent. Well, that works for lambda calculi where holds strong normalization, but that not works for untyped lambda calculus or for untyped combinatorial logic, because untyped lambda calculus just has weak normalization property, not strong. Well, that's I think. Well, but let's talk about categorical model. Well, we need some categorical background. Well, some definitions. Monoidal category. Well, monoidal category is a category with big functor called tensor product and some object 1 called unit, and for all A, B, C we have these properties. In other words, objects of this category with units should produce a monoidal structure, and monoidal category is symmetrical if tensor product has commutativity property for all objects A, B. Well, we have also two very natural properties called triangle identity and pentagon identity, but slides are too small for these diagrams, but you may read about in more details in, for example, MacLean and Ellenberg textbook called Categories for a Working Mathematician, or in Ellenberg and Moore article called Categories with Product. Well, the second one definition, a lax monoidal functor between monoidal categories is a functor with the next national transformation there. Star and view, so called application property. Well, really, that's not hard. Lax monoidal functor has natural properties again with diagrams, and again you may read about these properties in Categories for Working Mathematician. What about applicative functor? Is a partisan definition from article called Constructing Applicative Functors. We have some symmetrical monoidal category. So applicative functor is the lax monoidal endofunctor with a natural transformation P from ID, identity functor, to K. So such that for all AB, the next diagram commutes. Okay? Well, by default, we will consider applicative functor K on some Cartesian closed category C. Well, just because category with terminal object and with finite product produce some monoidal structure on this category. Moreover, symmetric monoidal structure because finite product is commutative. You know? Well, what about soundness? Well, if terms are beta and eta equivalent, then their images in semantical translations are equal, so equal arrows, you know. Well, we need to take semantic translations from simply type lambda calculus to Cartesian closed category and add translation for our type and rules for K modality. Well, we have translation as usual for types, for contexts. Well, translation rules for types with arrow and cross are defined as usual with exponential and products. Again, slide is too small for them. And interpretation for model types. Well, we interpret as with applicative functor. And after that, we need to check a substitution in a model, but it's too long and too boring. Well, let's talk about better again about reduction rules. Well, at first, semantic translation. Well, if we have this arrow, then we can obtain translation for pure using natural transformation. The second one, I think that would be better if I draw one picture. So, we have evaluation arrow in Cartesian closed category, but we have also evaluation arrow obtained by natural transformation P. So, B A times A to KB. I call that P epsilon. Well, and on the other hand, we have star. A times so that diagram commutes just as composition. Very simple thinkers, I suppose. Well, after that, we need to check that this interpretation preserves beta rules and eta rules. Well, as I told before, we will not consider iter rules. That's too boring and really simple. Well, however, I forgot to, well, talk about this later. Well, verifying of the reduction rule in a categorical model. Well, let us consider, for example, homomorphism law as an example. So that's really not hard to check that this diagram commutes. Well, this square commutes as natural transformation, and this triangle commutes again as composition. Well, so that pentagon commutes to not rocket science, as I told before. Well, and what we need to do that this equality would be preserved in a model. We need to check that algebraically. Well, we should unfold application, we should unfold pure, and little magic, and that's okay. Well, completeness not proved yet, work in progress. So, future research. Well, I'm not going to talk about conclusions, so, because I have a lot to do. Well, in monad class, in modern Haskell or Idris, is obtained by inheritance from applicative class. In other words, we have the next definition. So, from a logical point of view, we have some system with the next model axioms. So, it's kind of extension of IEL minus two ways, but they are described syntactically two equivalent definitions of monads. Well, we may extend our type system by adding some rule for the third axiom for some monadic calculation system based on applicative functors. For example, join, well, or monadic binding. So that's monadic binding from Mogi meta language. So, well, I have a fistful of hypotheses. The first one is, if we add join rule in our type system, then Mogi meta language should be embedded. Well, the second one, our system with monadic binding, well, the second rule, is a non-conservative extension of a Mogi meta language. And the last one, that extension of this kind should be sound and complete for some complication of monoidal monad. Well, for example, we may add to the definition of applicative functor some natural transformation from monads called eta. Well, but at first I need to prove. I need to prove completeness. Well, that's the first and the most important to do. Well, that's future research for 2 or 3 years, I think. Well,
thank you.
Yeah, thank you for attention.
So I have a very naive question.
Mm-hmm.
What about IEL?
Well, about IEL, we have intuitionistic reflection, but I don't know what does it mean in categorical sense. But we may use axiom of consistency of knowledge called, well, not K bot is the same as K bot implies bot. Well, from a categorical point of view, that's a very natural limitation. So it means that our functor should preserve initial object. So in categorical logic, false is the initial object. So, and knowledge consistency is is about preserving by functor. But okay, that should be preserved, but I really don't know what that should give from computational point of view. So false is a void type. Well, but it's really not good to use void in Haskell. So that's well, I need to think about that. But IL minus, I think, more useful for these goals.
Yeah, look, to make it clear, so you have IEL minus, one thing, then you translate it in this kind of type theoretic setting, and then you use the categorical semantics, right? So you have like 3 levels.
Well,
your presentation was a little bit mixed.
It's a kind of Curry-Howard-Lambeck isomorphism for intuitionistic epistemic logic IL minus.
So one particular thing, why you need this lex structure? So natural transformation would represent
I need
of your modality. Right?
I need lex monoidal functor for application property. So I need
I didn't quite understand.
I need this star for interpretation of application, for star application.
So that.
Well.
So to make it distribute over your
Yeah.
product.
Yeah. Yeah. So as I told, you may watch on this picture. So. Well, I use distribute for tensor product, and after that we apply evaluation error obtained by natural transformation. So without star, we cannot get needed application.